on the cloud. So now it'll be recorded on the cloud. And let's start on the VMCTF3 server. And then to check with this, so now I just ran the cat proxelf maps, and you can see some instance of the address. And then I will run it again. Then you can see that although the address space for the bin cat, these are the same, but the address for the library space, for example, libc is at b7d93, but here libc is at b7d3a. So not that much difference, but a little bit of difference in the address. So the server randomizes the address space whenever the new program executes. So if we do it again and again, for example, b7d3a, next time was the b7d b8. So the address will be randomized or something like this. So this server is enabled with the Asrl, and then that means also the stack address will be changing. So if you put your shellcode on the stack address space, then that will move around with the random base address. So if you cannot guess the exact point of the shellcode, then you might fail on running your shellcode by pointing that to the with the return address. So all the Asrl challenges are dealing with such randomization, and we will learn how to avoid the defense and bypass that. We'll use a different account for this. And this will have the same setup as you guys. And then let's get into the week 4 directory. If you run fetch week 4, it will fetch all the challenges and also for the binary program, but not for this file. I'll put this shellcode to use it in my exploit script. I coded in like the week 3 directory on the VMCTF1 server and just copied and pasted on it. Yeah, maybe you can do the same thing for your convenience to use this shellcode in your Python script. And before starting, let's get to the ASL check directory first. And I will first run this ASRL check binary. And then what it does is like it runs the same program for 5 times. Then what it does is internally, it just print out one of the address of the variable in the stack, and then one of the heap object, and one of the library code address. And then we can see that on each execution, address is changing randomly. So the some part are fixed, for example, 0. The last 0 and then first BF, yeah, these are fixed, but some of the values in the middle are keep changing, and then that consists for like the randomization entropy for 2 to the 19, according to the slide that I provided for the lecture. Yeah, and if you just brute force this stack address for the one specific shellcode address, then your chance of the winning would be like the 1/500,000. Yeah. And then for the heap address space, addresses are changing, not the last 3 digits, but the first 4 digits are changing. Yeah. So it has like around the 13 bits of the entropy. So your chance for like the winning for like guessing one address again and again would be like 1/, excuse me, 8,000. And then for the library space, you can see more or less changing in the address. For example, last 3 digits are all same. And then first 2 digits are all same. So only these 3 digits are different. Yeah, but it will not change the top bits. So like if you run it again and again, you will only see D and E for the first this variable address byte. Then like its entropy would be like around 8 bits. No, 9 bits. So you can guess the correct address if you brute force it for at least 500 times. Yeah. So one question from Sean was how long would it take to just brute force it? So for example, for the stack space, if you want to brute force it, you need to at least run it for 500,000 times, but it could be 1 million times or something. Then like to think about it. Maybe we can check the time for program's execution, and then it takes like the 0.2 seconds. Then you need to run it for the 1 million times, then 2000 seconds, right? And it's around the 33 hours, but if it is like the 500,000, then 16 hours maybe. Yeah, so that would be the the effort that you should put if you want to brute force a stack address. But if you get to the libc address, then what it need is around the 512, maybe twice of that, 1024. Then it takes 2 seconds, right? Then that could be more feasible than like attacking the stack space. So if you want to do a brute force attack, I highly recommend using the libc, targeting the libc address, for example, targeting a specific address for the system function, and then keep running the program. Wait until like it luckily matches to the system and then run the program. And that's actually the ASRL challenge 6, because I enabled the full ASRL for that. So the only way you can break exploit the vulnerability is brute forcing. So please be wise. Maybe you can try the brute forcing stack address, but I highly recommend you to brute force the libc address space, because this is the weakest part. But that weakest part will be removed when we get to the 64-bit machine, because it has more address bits that we can randomize in between. So it will have around 28 bits of the entropy, which is far larger than the stack address space on 32-bit. Then like it may take like several months or years, yeah, to guess the address and then by the brute force attack. So ASRL is quite a cheap but efficient defense, because the runtime overhead in like a 64-bit machine was just 1%, and in 32-bit machine it's around 3%. The reason is like in the 32-bit machine we cannot access the instruction pointer, and we need to run call and pop to pop the return address to get the instruction pointer, and that actually adds a little bit of overhead. But 1 to 3%, but we can get this kind of the raising the bar for the attacker. For example, making attackers took like several years to attack the vulnerability. Then it's quite economic. So that's why modern systems are applying this defense. And then another characteristic about the ASRL is that, so I put the ASRL check 2 binary to show that the relative addressing between the object in the program will be the same, even if the base addresses got randomized per each execution. For example, this is a printing of the address in the stack local variable. So you can see that so I believe like this printout is quite wrong. Yeah, but the stack variable 1 and then stack variable 2, the address difference between these two. For example, let's do it. So this address minus the address of a var2 is 12. And then in the second run, address of the variable 1 minus address of the variable 2 is 12. So if we have like the one variable and the other variable and taking the address, the relative distance will remain the same regardless how the system randomized the code. And this is because the system does not randomize the internal structure of the program. What it does is just taking the program and then change the base address, and that's why all the relative addressing within the program will be all same. And that applies to the heap objects too. So from the second run, let's subtract the address of the heap 2 from address of the heap 1, that's 16. And from the first execution, if we do the same thing, that's 16 too. And for the libc addresses, the same principle applies. So suppose we know the address of the printf, then we can calculate the offset between the printf and the system like this, and then that will be consistent across the multiple run. So we have a different address of the printf, but we also have the different address of the system, but the relative distance between these two will be the same. And we will basically exploit this kind of the knowledge. So even if we have a randomized address space, the relative addressing between the sum of the among the objects are fixed. So if we can leak any kind of the address from the address space, then we can completely break the Asrl. So that's the implication of all these challenges and tutorial, and you will learn it step by step. And let's start with the Asrl challenge 1, and let's take a look at the source code first. So this is the source code, and it's quite simple. So maybe you can recall this as a simple buffer overflow, stack overflow SC challenge in week 3. Because in the main function, it will directly call input function, and then it has a buffer overflow vulnerability here. So it reads twice of the buff size, while the buffer size is just a buff size. So it's just a simple buffer overflow case. Maybe you want to upload your shellcode into stack space and then run it. But the problem is, so even if we check the security mechanisms in the target program, it does not have anything. So it has an executable stack area, so you can execute on it. But the problem is that the system is enabled with the Asrl. So the stack address will be changing per each execution. Yeah. But thankfully, because this challenge is the easiest one, what it does is that it will print the address of the buffer at here. Yeah. So what that means is that, so it will print out the address of the buffer in the stack. And then the stack is executable. Then if we put our shellcode on this buffer and then jumps to it, then we can run the shellcode. So this challenge is an artificial one, assuming that you know the address of the stack directly, then you can exploit the vulnerability and get the shell. And let's try to exploit this. So what we need to do in the program is we need to get this address and then fill the buffer with the shellcode and some padding, EBP, and then put the return address to point this buffer address to run the shellcode. And let's do that. So we need to import everything like this. And then we need to get a shellcode. So I just use my shellcode here. So we got the shellcode. And then we will run the aslr-1 program. Yeah. And so the program prints the 2 lines of the output. And then in the first line, we can get the address of the buffer. And let's get that in the program first. So we can use p.receive line to read one line and strip all the data as a first line, and then second line, it will be then we'll just print the first line. Then it will print out your buffer is at this one, and then we only need this part. So to do that, I will split the string with the space and then take the last one. So first line space, and then take the last one. And then I will change this as an hexadecimal integer value and get it as a buffer address. Then we can check if we got the value correctly by printing out again. So hex buffer address. And let's check we got the buffer address correctly. So this was the string, and then this is the value that I got. So that we got the buffer address correctly. And the next is to check with the where our buffer is to overwrite the return address. So in the input function, there's a read function and LEA minus ADA to EAX and then push. So this is the buffer, where the buffer is. And then we need to fill the buffer. So buffer is at the EBP minus ADA. So we will put our shellcode at the front, and then we will fill with A's for the 0x88 times minus length of the shellcode. By doing this, we can have our shellcode here, and then heading as up to this point, and then this will be EBP, because we started with the EBP minus 0x88, and then we filled the shellcode, and then padding is a 88 minus the length of the shellcode, so the entire length will be 88. Yeah, so we can fill for the save the EBP, and then return address. And we want to put the buffer address, which is the address pointing to the shellcode, yeah, as their return address. And let's send it. Then see how it works. Yeah. So because it will directly tell where the buffer address is, then we can put our shellcode in the buffer. And by using that address for jumping, then we can run the shellcode and get the privileged shell. Yeah. So maybe you guys would think like this challenge would be too easy because it will directly tell the shellcode at the buffer address. And the reason why I put this challenge is that the Asrl-2 is a slightly difficult version of this one. So after fully understanding how it works, so at least you need to interact with the program to get the address information to put your shellcode. So previously, without the Asrl, we can put shellcode anywhere in the stack. So we can use, what was that? Environment variable or argument vector or file name. Yeah, anywhere we can put the shellcode and then run it. But in this case, we need to put our shellcode to the specific address that we know to use that as the return address. Then let's move on to the Asrl-2 challenge and then check what it does. So I will first just run the Asrl-2 challenge, and then it says some of the string, and then like it will never know the buffer address directly to us, but what it will do is it will print out some of the address information. Yeah. And let's check the source code about like what are them. So in the main function, it calls input function, and in the input function, there is a calling of the check function. And what it does is like it prints out some of the string and print out lots of %p. Yeah. And then let's check what this is doing in our debugger later, but it will print out some of the addresses, and then we can have a chance to exploit the buffer overflow vulnerability here. And your task here is to infer the address of the buffer from the leaked value from this printf function. And let's see what kind of values are leaking from this printf. So to do that, I will open a session, then this, and then So I will run the debugger on the right side. Then maybe we can break at the check function to see like what kind of values are printed at here. Yeah. And then maybe we can set the breakpoint right at the printf. So then run it. Yeah. And then this is the debugging screen. And before doing this, I would like to draw some of the diagram here. So for example, in this backtrace stack, we can see that there is a main function, and then there is an input function, and then there is a check function. And then we can think about some of the stack diagram. So there could be EBP of the main. It will point to the somewhere in the stack. And then before calling input function, ESP of the main should point to somewhere in the stack. You can regard each line as some of the stack space. Then it will put the return address somewhere in main, because after running the input function, it should return to somewhere in the main function. So it will store the return address of the input function here, and then save the EBP, which is the same value as the EBP of main. And then that will be pointed by EBP of input function. Then there will be ESP of the input function, and the value could be something. And there will be return address somewhere, input function, and then EBP of check function start. And then it will save the EBP, which is EBP of input function. Yeah. And then there could be ESP of the check function. And what it does is, so we break that the calling of the printf function, and before doing this, it will push one argument. So right on the stack, we have one argument. Let's see that on the debugger. So we push it to this string. So the string value, address value, 80485E0. This will be at the stack top. And then it will call printf. So it will store the return address of check function, which is this one, the next instruction of the call. And then it will have EBP of printf, and we'll save the EBP of check function. Then some of the local variables of the printf, and then it will have ESP here. And the important thing here is that what this printf is doing is printing something, and then print lots of %p on it. And then the weird thing is that, like in a while, it waits for some of the arguments, but we didn't supply any kind of arguments except for this string. Then how this printf will work? So printf is a special function that does not have the fixed number of the arguments to call the function. So for example, we can call it like printf %p buff, then it will print out the buffer address, but we can also supply another %p to get the address of the buffer, something like this. Yeah, and then we can call it again, we can push the argument again and again like this. So we can have an unlimited number of the arguments for the printf. And then if we supply just one argument and do not supply any other arguments in here, then what printf will do is it will regard that there is an argument. So although the first argument is here, this print p, %p will print out some of the data in the stack at here, and then second print %p will print out this one, and then it will print out the stack contents on and on. Then you can eventually print out the saved EBP value of the input function. Yeah. And then what that means is that if you know the saved EBP of the input function, so EBP minus saved EBP of the input function minus 0x88, there's where our buffer is. So if you can leak this value, then this value minus 0x88, then you can get the buffer address. And we will do that. And let's find that in this GDB first. Yeah. So to do that, we can start with the input function, and we can stop at before calling printf. So this address. So we can break it here and then run the program. Yeah. Then right now, no, my bad. Let's kill the GDB and then run it again. And then we will break at the before calling the check function. Yeah. And then this one. And run it. So this is right before the calling the check function. And then by doing SI, we can get into there. Yeah. And then it will push EBP. So now our stack has the saved EBP here. Yeah. So the saved EBP value will be this one, BFF47768 for now. Yeah. And then you cannot use this address directly because the address will be randomized across each execution. So just keep this in mind for as a reference of the address. And then, so it will call printf, but let's check the stack status. Maybe I can print out 30. So right now, this will be the first argument of the printf, because we break at the right before calling printf, and then this will be second argument, third argument, fourth argument, yeah, fifth, sixth, and on. Yeah. So what this means is that so although we do not have any kind of arguments, it will print out these values. So for example, so just to memorize the B7EC1000, and then I will just copy it. Yeah, these two values. And then by the next instruction, it has run the printf. And then let's check what has been printed by the printf call. Then it will leak the second argument, third argument, and then fourth argument. So what it does is it will leaking the values on the stack. Yeah. And then in the previous execution, we checked the saved EBP of the, where is it? Yeah. Save the EBP of the input function as a BFF47768. Then can you see that value at here? BFF47768. That's the saved EBP value. And then if you subtract this value by 0x88, then we can get the buffer address. And this is the logic behind how you can figure out like what kind of values are printed by the printf function. But I will guide you on like how you can get the offset more easily with some of the tools in the Pwn tools. So the basic is that on each of the execution, the address will be changing, but there will be a fixed offset, and then the printf function will leak some of the address values. And then we will calculate some of the relative distance between the buffer address and the leaked address. And if anything is fixed, then we will take that as some of the indicator for the some of the address in the stack, and we will subtract the offset to get the buffer address. That's the exploit sketch. And let's write the exploit, but I will just copy the exploit script from aslr-1. And we will run for the aslr-2. And then in aslr-2, we have 1, 2, 3 lines. So I will receive 3 lines, and then the line that contains the address is this one. And for this one, I will split it by the column and strip it, and then split it with the space again. So for the address line, I will split it as a column first, and then strip it, and then split it as a white space, and then text addresses. Okay. All right, I need to get the last object after the splitting the string. Then we can get these kind of the text address, and we need to change all these address as an integer, and then there's a nil. Then how can we convert this is so we will skip the nil string, but we will put all the integer addresses like that. And then for address in int, check we did it correctly or not. So I will print out the hex of the address in the int addresses array. Then we did it correctly. And then now we know that this one, the second value is the saved ABP, but I will go for some of the interesting way that you can find some fixed offset between the buffer. Yeah. And how to do that is that, so in Pwn tools, there's a function called cyclic. And what it does is like it will generate some of the random string, and not a random, but some of the fixed string that you can search for that string as a signature for the length that you supply. For example, if I create a string as a cyclic 50, and then if we print that, it will generate AAA, BAAA, CAA, this kind of the string increasing with the 4 byte 4 byte string, and then it will generate up to 50 characters as I supply that address 50. And then what I will do is, so I will send this string to the process. So, and then maybe 200, and then I will send this string to this, no, maybe 188 plus 8. So just overriding the return address, and then this will crash because we didn't supply correct return address at all. But after the process crashes, so we can do t.wait to see that the wait until the process crashes. Then we will open the core file. And what we will do is core.stack.find. We will find the address of our buffer because we put this cyclic string into our buffer. If we do core.stack.find, then it will automatically find where our buffer is. And then we will get the buffer address like this. And then I will print out this value. And let's run it. So these are just the translated input from the program. And then this is the value printed by the buffer address as it has crashed on like the sum of the BAA something, right? Yeah. So from the core file, we can get the buffer address. And there was one question. Yeah, why +8? So for +8 here is that we know the buffer size is 88. So from this one. So we did the reverse engineering, and then from the input function, we know that the buffer is at the EBP minus 88. So we fill the 88 bytes, and then the other 8 bytes are filling the saved EBP and the return address. And what we just did is like we intentionally crashed the program. And to do that, what we need to do is just overwriting return address to some of the random value. Yeah, and that's why I just use cyclic. So +8 comes from like the overriding these EBP and the EIP part. Yeah, right. So after having the buffer address, what we will gonna do is for the addresses that we collect from the leak, we will subtract the buffer address and then print that. Yeah. So what we are doing is like from the address leaked from the program, we will get the relative distance from that address to the buffer. So I will just run it. And then, so some of the values are printed, and then we are definitely seeing the 88 here. And then if we run it again, some of the values were changing, but the value 88 will never changes. That means because we get the saved EBP of the input function, then it will be always like the saved EBP of the input function minus the 0x88 will be the buffer address. So you can easily get from the leaked address which one is have the fixed relative address. Is that by generating a crash and read that from the core file and search for the buffer address at that time, and then you can subtract the value to get the offset and run it multiple times to check if like that address that offset is fixed. So this one was the printed buffer address, and then these are the address array. So now we know that the second item minus 0x88 will be the buffer address. Then what we will do is we will just copy all these things. So we will run the program again and then parse the int address. And right now we know that our target buffer address is the second item of the address, minus 0x88. That's our buffer address. And after knowing the buffer address, we will fill the buffer as a shellcode. And then we know the length as an 88, so fill all the bytes up to 0x88 bytes, then save the EVP and the return address. And it will return to the buffer address if this address is correct. So let's run it. No. I made a typo. This int addrs, right? Yeah, from the address array that we collected from the output. Yeah, we will choose the second one and then use that as a buffer address. Then it worked. So the important thing is that the relative addressing between the one of the local variable and save the EBP or some other values in the stack some other addresses stored into the stack, then you could find some of the fixed offset. So the lesson here is that if you have any kind of the memory leak, information leak about some of the addresses, then attackers may figure out like how some of the fixed offset between the leaked address and the buffer address, then they can utilize that to bypass the Asrl. Any questions for this challenge? So the challenge aslr-1, it directly tells us like the buffer address, but for the challenge aslr-2, it does not tell the address directly, but from the address leaked from the stack, we can infer where the buffer is and utilize that. Then let's move on to aslr-3. And this is a slightly modified version of the aslr-2 challenge. And what it does is, in the main function, it calls the input function, and in the input function, so it will ask for our the buffer overflow case first, so we can launch buffer overflow attack here, and then after that, it will say how many bytes of your name do you want to print, and we can supply the size as I, then it will write from the buffer. And what this means is that, so it will leak some of the values on the stack, for example. So because this is another stack overflow case, because this is actually the stack overflow for by the reading the more data than the buffer size. And then this is a stack overread by supplying the bigger I. So you can choose any kind of I here. Yeah. Then bigger size, bigger than the buffer size, then it will print out some of the values on the stack. So for example, what we can do is maybe we can supply 202i. Yeah. Then what it will do is it will have the mains EBP. Mains EBP will point to somewhere in this store some saved EBP here. Then there could be the return address in libc start main. Then somewhere ESP of a main, it will be here, and then call the input function. So return address in main, and then in the input function, EBP of I will be here, and then save the EBP of main, and then there will be a write function called here, and then there is a buffer. Maybe let's check where the buffer is first. So from the read function, buffer is at the EBP minus 0x88. So at the EBP I minus 0x88, we have a buffer here. Then what this write function, if we supply 200, is doing here is that it will print out all these bytes, because 88 is just 136, right? 136, and it will print out all the values up to save the EBP, and then it will print out 64 more bytes from the stack. So maybe we can get the address of the save the EBP, yeah, of the main function, even if we overwrite the return address here. Yeah. So what that means is that, so I will just type a simple value. So I will just type 2 for the name because I will not trigger the buffer overflow here, but I will type 200 to trigger the buffer overread. Then it will print out some of the data in the stack like this. Maybe we can utilize that. And right now we don't know what these values are. And if we print out something like this, then we can see that some of the output would be the address of the stack. And if we can get any kind of the address that has a fixed distance to the buffer address, then you can utilize that. So please try to apply the knowledge that you learned from Asrl-2 to this kind of the to attack this program. And one of the caveat about doing this is that, so for instance, so previously it was easy to parse the string because all the values were printed as a string value. So what we can do is split with the colon and then split with the space. But at this time, what we can do is, so if we do run the aslr-3, then type simple name, then 200, then it will print out the 200 bytes. So what we can do is read 3 lines and then read 2 lines and then supply 1 character and then read 1 more lines and then supply 200 and then read the data. So read 2 lines, supply 1 character, and then read the 3rd line. Maybe I can just reuse this one. Then print 1st line. And then I will just put 200, for example. So we need to overrun the buffer. So you need to fill the bigger size than the buffer. Maybe you can put 500 if required to leak another saved EVP or other stack addresses from the program. Yeah. And then this is what you can do. And after doing that, you need to read the data. And then the data might be maybe just reading 200 data. And we can print out that here and then quit the program at here. And I need to change the program name as a aslr-3. My bad. It should be character 3 and then character 200. So these are the address values that we have read, but the problem is that these are binary bytes. And then we need to read these as a 4-byte data and to represent that as an address. And how can you do that is, so for so we will split it as a 4-byte. So data I multiplied by 4 up to I multiplied by plus 4. And then this will be first 4-byte of the data, right? So for each 4-byte, we can apply function u32. Then this will translate the character into the integer value. And then we can print this out as a hex value, something like this. So now the challenge would be look like a similar to the aslr-2 if we just finish this part. And to use the core dump trick, yeah, what I will do is I will just fill 0x88 plus 8 bytes, yeah, and then it will have a loss of 3 and then crash, and then we can also get the addresses before crashing it. So after doing this, we will do p.wait, and let's copy some of the things that we did. And then from the core file, we will try to find 3 multiplied 0x88 plus 8, what we supplied for the buffer. Yeah. Then if we can see that, then we can get the buffer address. So from the core file, we can get the buffer address. And the next thing that we would like to do is for this kind of all the addresses, we would like to print out not the hex of address minus buffer address to get the relative distance from in the stack. So if we run that, so you see that the B0, 144, 14C, but the important thing is that we need to check if these values are consistent over across the multiple execution. So all the other values are changing. The value of the B0, 144, 14C, yeah, it's not changing. So you can easily get the maybe the 1, 2, 3, 4. So if you make it as in like the array, so for example, then after doing this, we find the fourth last item as the one with the offset 14C. So if we do int addrs minus 4 minus 0x14C, that will be the real buffer address. Then remove this part and hit so remove this part. I edited the wrong code, I believe. Yeah. So the right now, so I need to store addresses again here, and then int addrs append addr, yeah. And then we have it here. Yeah, sorry about that. And then the int addrs minus 4 will be the address of the this one, and then we will subtract 14C, and then that will be the new buffer address. Then I'll print out hex buffer address, and then print out hex new buffer address. So this address is retrieved from the GDB, and then this address is calculated by us, not using GDB, just to take a look at the output and then subtracting the value. And then these two values are the same, so we can use that value as the buffer address. Yeah. But another challenge of this one is that, so you can launch the buffer overflow attack at the first attempt, but after you supply all the buffer overflow attack vector, then it will leak the address value. That means you can only know the address of your shellcode after running this point, but it will return. Then there will be no chance that you can exploit the value that you got from the leak. Did you all understood the point? So the important point here is that after you supply the buffer overflow attack vector, so you need to supply all the shellcode and then the return address. Then it will tell us about the buffer address. Not directly, but indirectly, we can calculate it. But even if we know where the buffer is, then there is no chance then that we can exploit this vulnerability again, because it will return. But please don't give up. There's a way that you can supply your first exploit vector to have the return address as the address of the info function. And that's possible because this program is an executable file, which is not randomizing the code and data section for the program itself. So that's fixed. So the address of this input function is fixed. So how you can design your exploit is that in the first exploit, you can write up to 0x88 bytes, and then 4 more bytes for the saved ABP, and then write the address of the info function as the return address. Then, after leaking the addresses, you can calculate the sum of the buffer address, and then it will return to the input function again. Then you can exploit this vulnerability one more time. Then you can use your leaked data to exploit the vulnerability and jumps to your shellcode. Any question for like this part in aslr-3? So basically, the challenge is very similar to aslr-2, but it has 2 additional steps. One is you need to interpret the binary stream data as an address, as addresses by using U32, that kind of the script function. And also, you need to return to the input function again to exploit this vulnerability twice. And then we are at like a 404. So I will give a quick overview on like how you can solve aslr-4, and then give a little hint about aslr-5 and 6. So for aslr-4, what this is doing is in the main function, it runs a set reUID for us. So what we need to do is like just running the so it's running the system function. And then what it does is like it actually gets the address of the printf. Yeah. And then in the input function, it will tell us where the printf address is. And we can utilize this leak to launch the system function at here. And to do that in real quick, how you can do that is right now, at this point, we don't need any kind of shellcode at all. So what we will do is so we will open the aslr-4 process, and then we will read the first line. Then the first line contains the address of the printf at the end. So we will strip it and then split it with the space and then take the last one. So check if we got the address of printf correctly. So no, not hex. So this is the address of the printf, and then we will get the address of the printf from this text file by translating it as a hexadecimal integer. So now we have the address of the printf here, and then note that the relative address between the printf and the system will be the fixed. So by just knowing the address of the printf, we can get the address of the system if we have the binary for the library. So because this printf function resides in the libc, the standard C library. And to check where that file is, you can run ldd aslr-4, then it will tell where the libc.so.6, the libc file is, and you can open it with gdb. Then you can print printf, print system, and you can subtract these two values to get the offset. And you can even do that in the pawn tools. So there is a function called elf. So just copy this directory and then open this as an elf object, and then offset printf is at either symbols printf, and then offset system is at either symbols system. And what we will do is distance between printf and system is printf offset printf minus offset system. And then let's print the value. So the distance between the printf and the system is 59,600, and that's the fixed value across the multiple running. And what we will do is from the address printf, we will subtract distance between printf and system. And that will be the address of the system. Let's check it. So it just calculated the projected the address of the system, but to check that, you can also print out the print of the offset printf and then print of offset system. And then if you do it correctly, then the sum of, so I need to apply hex on this. So because it aligns by the page size, which is the 1000, so the last 3 digits of the address space need to be same. Yeah. So this will be the printf address because the address last 3 digit of the printf is 680, and then last 3 digit of the db0 will be for the system. And since we calculate the address correctly, then let's check where the buffer is. Buffer is at the EBP minus 88. So what we can do is we can supply the buffer as a multiplied by 0x88, and then put blah on it, and then the return address as a address of the system. And then we need to supply arguments. So we skip the next 4 bytes, and then the first arguments need to be here. So in that case, we need to have some sort of the address of the string to run the program in there. Yeah, but think about all the address space are keep randomizing. So we also need to figure out some of the string from the relative addressing from the system. And I will guide you on how you can do that easily. So what you can do is run gdb and then with the aslr-4 and break and main, and then run it. The reason why we need to run it is like the running will load the library code. So after running the program, we can get the address of the system in the gdb. And then what we'll basically do is, so we will search for some of the string starting from the system address. nothing useful, nothing useful. And here, yeah, maybe we can use this as a string, but the address of this one, yeah, the @, yeah. And then let's calculate the distance between the address of the system and to that one, yeah. So we'll get that. So now we have this offset, and then if we add this offset from the address of the system, then we can get the address of the string @. So so because the relative addressing will be the same, so we found the sum of the @ from the sum of the distance between that sign from the system and the one instance, and then that will be fixed across the randomizing. So if we add something like this, then it will call system with the @ if we put like this. Then we will basically send buffer and then theta interactive. Maybe it's wrong. It says like this part was wrong. We need to apply p32 to the address @ because we need to make all the things as a byte string. And by running it, so it says @ is not found. And after having this step, you can create a path. You can adjust the path environment variable, and to make that @ file as a shell, then you can get the shell with the in the privileged space. And then to give a little more hint about the Asrl-5, this challenge is another variant of the, actually it's a combination of the Asrl-2 and 3. So what it does is like it will not let you know anything, just get the buffer overflow vulnerability and then exit. Then at the first attack, you can call the check function, yeah, to leak some of the data. And then you can control that to return to the input function again. Then you can use the calculated address for the exploiting the buffer overflow again at here. So make sure that the code addresses are fixed here. So in Asrl-5, you need to first return to check function, and then it should return to input function again, then utilize the leaked address value to get where the buffer is. Then the challenge will be very similar to Asrl-2. The last challenge is Asrl-6, and the difference of this challenge is that, so if you take a look at the source code, then you will see that the source code is exactly same as the Asrl-5. But the problem is that in this case, I applied the full Asrl, so all the addresses are randomized. That means, so if you read the header of the read-elf, then it says dynamic shared object, and then its entry point is not starting with the 80 something, and then just a 580. That means the address of the functions will be changing on each time. So once at certain time, like it was at the 4337 AF for the main, and then at the second time 4247 AF, 48B7 AF. So code addresses are also changing. So in Asrl-5, how you can exploit this one is like the calling check function first and then input function again. But at this time, you cannot guess where these functions are. Yeah. So in this case, the only way to exploit this is with the brute force attack. And please note that the library space has the smallest entropy pool. So you could have a winning chance of 1/512 executions. So please write your full exploit chain based on the one system function call, or no, actually you need to call exec VE, yeah, one exec VE call to inherit the privilege and also run the shell, yeah. And please collect all the addresses from the one instance, and then like run that for multiple times. Then you can eventually get the shell out of the brute force attack. And this is the end of the tutorial for Asrl-6. And if there's any question, I'm happy to answer. Yeah, if you. Maybe there's no question for now. Then please post your question on Discord or message me or Philip when you're stuck on some of the challenge. But please remind that the Asrl challenges, you need to know about having the knowledge about the address space, then utilize that to figure out like what your target address is, for example, pinpointing the buffer address or getting the address of the system or other functions. And because the relative addressings are fixed, so you can utilize that and exploit the variability. But the important thing is like you need to do leak first, then exploit. And in Asrl-3 and 5, it's quite upside down. So it will let you exploit first, then leak. Then in that case, you can return to the exploitable function again to have a chance like exploit after the leak.